Hey guys, tonight we glide past the moon's silver face, past the rusted breath of Mars, and even past Jupiter's heavy storms, until your spacecraft slows, drifting towards something impossibly strange in the velvet dark. Ahead lies a planet no bigger than Jupiter, yet its surface sparkles faintly, like a gemstone dropped in the deepest well. It orbits a dead star, so tightly and quickly that a year lasts barely more than 2 Earth hours. You squint. Are you imagining things? Or is that entire planet made of diamond? You are not imagining it. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as always, I'd love to know where you're listening from and what time it is. There, drop it in the comments. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. As you approach the glittering sphere, there's something unsettling in your stomach. Maybe it's the way the stars behind it shimmer oddly, like light bending around glass. Maybe it's the silence of this dead part of space, far from Earth, past the galactic suburbs, but mostly it's the realization that this planet, PSR J1719 1438b, if you're feeling formal, isn't just made of some diamond. It is diamond. Kind of, you ease closer, imagining what it must have taken to create something like this. Not a clever alchemist in a cave, not a coal seam under pressure. No, this story begins with a massive star one, far larger than our sun burning bright billions of years ago. You can almost hear its nuclear roar in your imagination. Helium fusing into carbon, carbon into heavier elements, a cosmic forge, hurling out radiation and light. Eventually, the star grew unstable, like all giants. It didn't go quietly. It swelled, coughed off layers, and collapsed into itself in a breathtaking finale of gravitational despair. If it had been slightly more massive, it might have become a neutron star or even a black hole. But it stopped just short cooling into a dense white dwarf. Now, here's the weird bit. When white dwarfs cool and the temperature drops far enough, the carbon inside begins to crystallize. That's right, cooling stars become diamonds. The idea was once fringe science fiction, but in 2004, astronomers spotted evidence of this very process. The star BPM 37103, lovingly nicknamed Lucy after the Beatles song, is thought to be an enormous crystallized carbon mass, a literal diamond the size of Earth, floating in space, and your glittering destination. It's weirder still, it used to be a star too, but its matter was siphoned away by a nearby pulsar, a fast-spinning neutron star that gobbled its neighbor like a hungry blender. All that remained of the companion was its dense core, carbon, mostly. The leftover nugget now shrunk into a planet-sized object, orbiting that ravenous pulsar. You float there in your imaginary suit, watching the diamond planet turn. It reflects just a whisper of the pulsar's harsh light. From this distance, you see no mountains or oceans, no clouds or auroras, just a hard surface, glinting like frosted glass under a dying lamp. Somewhere in the distance, your brain pokes you. Hey, remember how diamonds are formed on Earth? You do. Carbon under extreme heat and pressure, deep underground, for a very long time. The same principle applies here, just multiplied. A white dwarf is unimaginably dense. 1 sugar cube's worth of its matter would outweigh a truck. The pressure inside, millions of times greater than anything on Earth. You're not just looking at a big jewel, you're looking at a dead star's heart, squeezed until it crystallized into one of the rarest, most valuable materials we know, on a scale that would bankrupt the entire jewelry industry if you somehow hauled it home. Of course, hauling it home isn't an option. For one, it's 4 light years away. For another, if you got within orbit without protection, the radiation from the pulsar would shred your DNA faster than you can say space SPF. Even your atoms might get gently rearranged. Still, it's tempting, isn't it? A planet made of diamond, not metaphorically, not poetically, physically, and you, floating beside it like a speck of dust near a chandelier. Historians, funnily enough, have always associated gems with power. Cleopatra bathed in crushed pearls. Medieval kings embedded jewels in their crowns, their swords, even their dining utensils. But even the grandest sultans couldn't dream of this. They thought heaven was paved with gold. Turns out, it's way cooler. Carbon latticework, reflecting X-rays in the dark. Some fringe thinkers have even toyed with the idea that if civilizations exist out there, they might treat planets like this as temples, banks, or sacred sites. Sure, there's no evidence, but when you're talking about billion-carat diamonds in space, normal rules bend a little, so you float, and you wonder, if this is what happens when a star dies, what else is waiting out here? What other strange, poetic leftovers has the galaxy cooked up? Behind you, the pulsar blinks 31 times per second, a cosmic metronome beating time in this forgotten corner of the universe. Ahead, the diamond planet spins in silence, shimmering softly in a place that should have been nothing at all. And you're just getting started. You float in stillness, but the story doesn't, because this diamond planet, this quiet sparkle in the dark, didn't form overnight. Its birth took billions of years, and a cocktail of cosmic forces that would terrify any sane geologist. You're about to take the scenic route through time, all the way back to when this gleaming world was just a whisper inside a raging star. Start by rewinding the universe. Fast. Stars flicker backward into gas clouds, galaxies unspin, planets get unmade, and somewhere, about 11 billion years ago, a massive star 8, maybe 10 times heavier than our sun, comes into being. It lights up quickly. Stars that big don't mess around. They burn fast, they burn hot, and they don't burn for long. This one devours its hydrogen in a few million years. Just a blink. Cosmically speaking, you, watching from a safe imaginary distance, can see the outer layers expand and pulse, as if the star knows what's coming. Inside, heavier elements are forming: helium, carbon, oxygen. At some point, the star swells into a red giant, so bloated that it could swallow Earth and Mars in a single gulp. You gulp reflexively just thinking about it. Then comes the finale. The core collapses. The outer layers are hurled away in a massive supernova, maybe even blasting nearby systems with enough radiation to sterilize a planet or two. But our star isn't powerful enough to become a black hole. Instead, what's left is a white dwarf, a super-dense ball of carbon and oxygen, still glowing with leftover heat, like a coal after a campfire dies. Over time, that white dwarf cools very slowly. It takes billions of years, but eventually the atoms inside begin to lock into a crystalline structure. That's right, this dead star doesn't just contain diamond. It becomes one. Mainstream science only confirmed this idea relatively recently. For decades, astronomers debated whether white dwarfs really crystallized. Then in 2004, observations of BPM 37093, nicknamed Lucy, showed seismic vibrations consistent with a crystalline carbon structure. You remember Lucy now, don't you? The Earth-sized diamond with a Beatles name. But PSR, J1sensin19 Wangsino 38b, that's a different flavor of bizarre. It wasn't just a white dwarf. It got eaten. That's where things start to sparkle sideways. You see, nearby was a pulsar. Imagine a neutron star, spinning rapidly, shooting out beams of radiation like a cosmic lighthouse. This one spins 10 Dorito times faster than a kitchen blender. It used to be part of a binary system. Two stars dancing close, exchanging heat, light, and eventually matter Our white dwarf wasn't just a passive partner. It got pulled in, slowly stripped by the pulsar's immense gravity, not yanked apart in one go, no. This was a long, grim dinner date. Bit by bit, the white dwarf lost its outer layers until only the dense, carbon-rich core remained. What was left wasn't really a star anymore. It was too small to sustain fusion, but too massive to be just a planet. A cosmic in-between, but it orbited its predator, the pulsar, faithfully, tightly, fast. And so, a new object was born, a planet-sized remnant made mostly of crystalline carbon, orbiting a dead star. Technically, PSR J1719-1438b isn't a traditional planet. It's a degenerate remnant, a phrase that, let's face it, sounds like either an insult or an indie band. But that doesn't make it any less real. Historians of science still argue whether calling it a diamond planet is accurate or just great PR. Some say the structure isn't pure diamond. Others argue that it's likely too hot inside for a perfect lattice to form. Still, if you're going to nickname a thing that used to be a star, got stripped to its carbon bones, and now orbits a pulsar every 2 hours, diamond feels fair. Besides, the sparkle isn't just chemical, it's metaphoric, symbolic. This planet is what happens when time, pressure, gravity, and violent intimacy between stars play out to their logical end. You don't see it shimmer from Earth, but you feel it. Just knowing it's there, you float a little closer in your imaginary suit. There's no atmosphere, no light show, no surface breeze. Just a quiet, hardened orb, reflecting the pulses of its partner like a disco ball mourning its dance floor. And if you could take a chunk of it, just a cubic meter, you'd hold trillions of carats in your hand. That's assuming your hand didn't collapse under the gravity, or vaporize from the radiation, or get compressed into paste by the sheer density. So yes, your souvenir dreams may remain safely theoretical. Quirky thought of the night. If you were to propose marriage using a diamond from this planet, you'd probably need a forklift instead of a velvet box, and your partner's finger would either snap or enter orbit. Not ideal. Unless you're into astrophysical metaphors for love. My love for you compresses time and space sounds poetic until the ER visit, and so the timeline clicks forward. Billions of years of star birth, collapse, cooling, and cannibalism, all so that one day, on a small blue planet far away, you could lie in bed and listen to a story about a place where a star became a gem, and a gem became a ghostly world. The stars don't just burn and die. Sometimes they crystallize, and sometimes they sparkle. You're drifting in orbit now, still weightless, but not without a sense of gravity, figuratively and very literally. Below you spins a world born from collapse, pressure, and relentless time, and at the heart of its story is a gift, though not one you'd ever want unwrapped. This gift came from a star that didn't just burn out, it was crushed. Let's look closer at the giver of this jewel world, the pulsar. That name alone sounds like something that could zap you into a cloud of atoms, and honestly, it kind of could. Pulsars are neutron stars, and neutron stars are terrifying. They're born when stars so massive they practically swagger across the cosmos, reach the end of their lives, and go supernova. What's left behind is unimaginably dense. How dense? Well, a teaspoon of neutron star material would weigh about 1 billion tons. You could try lifting it, but you'd probably just punch a hole straight through Earth. Now, our particular pulsar, PSR J1719-1438, is what astronomers call a millisecond pulsar. It rotates more than 10,000 times per minute. Let that sink in. This thing, about the size of a city, is spinning so fast that if it were a vinyl record, it would have shredded the needle. The player, and maybe half the planet trying to listen to it, It's also spewing out beams of radiation from its magnetic poles. Like cosmic lighthouses gone berserk, these beams flash toward Earth with such precision that astronomers use them to keep time more accurately than atomic clocks. It's like the universe built its own wristwatch, then set it spinning, but that's not the gift we're talking about. The real gift is what the pulsar took. You see, pulsars don't start spinning that fast on their own. They need fuel, and often that fuel is a friend, or, well, an X-star, which brings us back to the companion, the once mighty star that now twinkles below your feet as a compressed carbon sphere. The pulsar siphoned matter from its partner like a greedy guest who eats your cake and your candles too. Over time, it stripped away the outer hydrogen and helium layers, accelerating its own spin in the process. This is what scientists call recycling a pulsar, a term that sounds almost polite for what is essentially stellar cannibalism. What's left orbiting the pulsar is that stripped core, carbon-rich, heavy, compressed to the point of crystallization. Some models suggest it could be 99.9% pure carbon, and because of the immense pressure it's under, much of that carbon has likely aligned into diamond-like crystal lattices, not because the universe wanted to bling out a solar system, but because that's what physics does under such hellish circumstances. There's an eerie elegance to it. You're essentially looking at the skeletal remains of a sun, polished by gravity until it shines, a diamond not cut by human hands, but by time, collapse, and violent proximity to a cosmic engine. Historians, well, at least the more poetic ones, might call this a kind of galactic memento mori, a reminder that even in death, stars can give something beautiful, even if that beauty comes at the cost of annihilation. Now here's where things get fringe. A few speculative physicists have floated the idea that this type of object, dense, dead, and rich in carbon, might not be unique, that there could be many such X-stars drifting out there, too small to reignite, too dense to crumble, quietly orbiting their killers. Some even argue that a good number of rogue planetary objects, the kind that don't orbit any star, might be failed diamond cores like this one. It's not exactly accepted mainstream science, but hey, in space, the line between genius and bonkers often rides a photon, the sparkle. By the way, it's real, but not like what you'd see in a jewelry store. This isn't fire under a spotlight. This is radiation glinting off a hard, lightless surface from Earth. You wouldn't see it with your eyes, but the pulses bouncing off this thing, microwaves, X-rays, and gamma bursts, suggest its reflective qualities are nothing short of dazzling. Just not in the usual spectrum. You imagine the view if your helmet could detect radiation. It would be like looking at a disco ball made of pain, dazzling beams carving sharp edges into the void, bouncing erratically off a surface designed by physics, not artisans. So, what is the true gift from this dead star? Is it the diamond-like planet, the record-breaking pulsar spin, or is it the story, the cosmic drama of a system that devoured itself to become something beautiful? You float there, and the answer doesn't come easily, because the galaxy is rarely kind. But sometimes it's accidentally poetic. There's one more twist. The orbit. This planet doesn't lazily circle its pulsar the way Earth dances around the sun. Nope. It completes one full orbit in two Earth hours. That means it's very close. So close that tidal forces likely stretch it into a slightly distorted shape, maybe even teardrop-shaped, which is fitting, isn't it? A jewel carved from heartbreak. But what keeps it there? Why doesn't it spiral in and vanish? Simple angular momentum. That spinning neutron star may be a glutton, but it's also a balance artist, like a figure skater spinning faster by pulling their arms in. The pulse's gravity pulls tight on its companion, locking it into a perfect, terrifying ballet. And you, the floating observer, realize just how much choreography goes into the universe's most dazzling horrors. One gift, one death, one glittering afterlife. You've heard of planets forming from dust, gas, ice all swirling around newborn stars like kids at a birthday party. But this planet, PSR J719 or 238b, oh no, this planet was never invited to that party. It used to be the party, a full-blown star in its own right, burning bright before its slow, spectacular fall. And now it's this, a husk, a relic, a strange little leftover twinkling beside a cosmic metronome. But how did it get here to this point of no return, spinning just 600 kilometers from its captor? Let's rewind one more time, just a few billion years. Back when this system was young, well, younger, there were two stars, one slightly larger than the other. They danced together, locked by gravity, each tugging gently at the other's edges like dancers in a slow, burning waltz. Over time, one star exploded. It didn't vanish, though it collapsed, becoming that super-dense pulsar you met earlier, PSR J719 and the surviving star, it didn't exactly get to live happily ever after. Instead, the pulsar began stealing, bit by bit, like a picky eater nibbling only the frosting from a cake. It pulled matter off the companion star's surface. Hydrogen, helium, all gone. The core grew smaller, denser, until what was left couldn't be called a star anymore. It became a crystallized corpse, still orbiting, too heavy to flee, too light to fight back. This is what PSR J1719-1438b is today. It's not a planet in the traditional sense. It's what astronomers call an ultra-low-mass, white dwarf remnant, but that's a mouthful, and way less fun to say than Diamond Planet. So let's keep the sparkle. Now comes the real kicker. This X-star turned planet orbits its pulsar so tightly, it completes a full revolution every 2 hours and 10 minutes. That's about how long it takes you to watch a movie and scroll through your phone halfway through. That's its year. You blink, it's orbited again, and here's where things get wonderfully unnerving. The gravitational tug at that distance is immense. One misstep, one micro glitch in orbital math, and this planet would be shredded into a glowing debris ring. You don't get orbital room for error when you're parked next to a celestial blender. It's fast, too. You hover near it now, still in your quiet, imaginary ship, watching it spin around the pulsar like it's in a rush. Scientists estimate it's moving at over 700 kilometers per hour. You know what else moves that fast? Nothing in your life. That's 500 times faster than a commercial airliner. Blink, and it's halfway through another orbit. Now, you're probably wondering how scientists even found this thing. It's not like it glows in the dark. It doesn't beam signals or show up in your backyard telescope. So how? They listened. Because pulsars, remember, don't just spin, they pulse over and over again, like the universe's own broken alarm clock. And scientists noticed that this one, its pulses were off, just slightly, just enough to suggest something was tugging at it. A gravitational hitch, a timing irregularity, something tiny, but massive enough to affect a neutron star. And that something, after a lot of calculations and probably a few gallons of coffee, turned out to be PSR J1719-1438b. Here's a wild detail for your dreams tonight. Scientists never saw the planet, not directly. What they saw were delays in the pulses, tiny variations in milliseconds that told them, hey, there's a companion here. Like seeing a shadow before you see the person, or hearing footfalls before the door opens. That's how we discovered the Diamond Planet, not with our eyes, with patience, math, and a cosmic game of echolocation. Historians of science often debate when astronomy stopped being about looking and became about listening. Some say it started with pulsar timing like this. Others point to gravitational wave detection. Either way, PSR J119111438b stands as a perfect example of science hearing what it cannot see. You look again at the planet, spinning quietly below you, caught in a gravity well so deep it might as well be destiny, and you wonder if it had feelings. Would it want to break free? Or is this just what afterlives look like in space? Some fringe thinkers even suggest these diamond remnants might be more common than we thought, that there could be entire rogue systems of stellar corpses orbiting one another in silent loops, long after their light has gone out. It's a haunting idea. Whole systems too quiet to detect, too cold to glow, just out there, spinning. You feel a chill, even in your imagination. And then you remember, this is the galaxy's version of a love story. A violent one, sure, but what else is gravity if not obsession? One star devoured the other, but it couldn't bear to let it go. So it kept it close, forever. You're still there hovering, just outside the gravitational cling of a collapsed romance. The diamond planet below is silent. It doesn't rotate with a dramatic wobble. It doesn't erupt in flares or shimmer in colors your eyes can see. And yet, it gleams in your imagination like a polished mirror held up to the cosmos. But is it really diamond? And if so, how do we even know that? First off, let's get one thing straight. No one flew out there, cracked open the crust, and said, "Yep, that's definitely a 5. So a mile-wide engagement ring. All of this is deduction, science fiction level deduction. Maybe, but grounded in math, models, and a suspiciously twitchy pulsar. So how did we arrive at the diamond planet label? Astronomers began by calculating the mass and size of PSR J177191438b based on the effect it had on its pulsar partner. The pulses from PSR J177191138, the parent neutron star, arrive like clockwork. Except they weren't. Tiny variations hinted that something small, yet heavy, was yanking the pulse's arm. From this, scientists inferred the presence of a companion object. Now here's where things get juicy. The mass of the object was roughly equal to that of Jupiter, but its radius much smaller. That meant it had to be far denser than any gas giant. And dense matter is what happens when atoms get pushed so close together that they stop caring about personal space. At that point, astronomers knew they were looking at something unusual, an object with the mass of a gas giant, but the volume and structure of something closer to a crystal. And not just any crystal, one made of carbon, under immense pressure. And that, my friend, is pretty much the definition of diamond. You might think of diamonds as rare, but in the universe, carbon is abundant. It's the 4th most common element, and under the right conditions, say, inside a white dwarf remnant, with enough time, gravity, and a hint of desperation, it crystallizes into diamond. In fact, there are giant diamond cores hiding all over the cosmos. Our own sun, when it dies, will likely become a white dwarf, and if it cools long enough, say, over the course of 1 trillion years, its core might eventually crystallize too. So the far, unfathomably far future could be full of dead, glowing, Earth-sized diamonds just chilling in space. You'd think that would crash the gemstone market, but thankfully, no one's figured out how to fly a pickup truck full of diamonds across a light year. Yet, here's where it gets murky. Some scientists caution against calling PSR J177191438b a diamond planet in the way that might make jewelers swoon. The structure may not be a perfect single crystal lattice. It could be polycrystalline, irregular, or even amorphous in parts. There's debate over how complete the crystallization process is and whether temperature and gravity balance would permit diamond purity throughout. So yes, it's probably made mostly of diamond-like carbon under pressure. But no, it's not a shiny cut gemstone hanging in space like an earring. Still, the sparkle is real, not in the visible spectrum, but in the idea, because when we say diamond, what we really mean is a material so compressed, so ordered at the atomic level, that it reflects light in specific ways, resists deformation, and endures more than almost anything else in the universe. And when it comes to cosmic metaphors, diamond is a great one. Historians once believed diamonds were literal tears of the gods. Ancient Greeks thought they were splinters of fallen stars. Turns out they weren't far off. Some fringe philosophers today wonder whether calling them precious stones was just our subconscious yearning for lost pieces of the universe. You glance down again at PSR J1119 1438b and try to imagine its surface. Would it be smooth, cracked like desert earth? Would there be jagged cliffs, glittering edges, or glassy stretches where light dances like it does across frozen lakes? Probably not. But you can dream. If you tried to land, you'd probably die before your boot touched down. The gravity's too high. The radiation's brutal. Your ship would pancake. Your atoms would be redistributed. But hypothetically, if you could step onto it, you'd be standing on compressed carbon, thousands of kilometers deep, gleaming, resilient, and unimaginably old. There are other theories. Of course, some argue the planet may be a mix of carbon and oxygen. Like many white dwarf cores, others suggest a thin layer of helium might linger, or trace metals fused during the original star's lifetime. Still others wonder if internal heat might prevent perfect crystallization at all. This is where the phrase scientists still argue comes in. Because they do. And honestly, would you trust a cosmic mystery that didn't cause at least a few academic brawls? But for now, we use the best model we have. A Jupiter mass object, too small to be a star, too dense to be a planet, spun around its pulsar in a blistering 2-hour year, and likely composed mostly of crystallized carbon, which we call, with a wink, diamond. So yes, it sparkles, not in the way a diamond on a ring does, but in the way a fact does. When it hovers on the edge between beauty and absurdity, between death and permanence, between fire and pressure and forever, you pull back slightly in your mind's eye, letting the pulsar's steady beat fade to a soft, cosmic heartbeat behind you. The diamond planet remains in view, still circling, still glinting with the kind of elegance only destruction can create. And suddenly, you understand this planet doesn't sparkle because it wants to. It sparkles because it has no choice. You float a little lower now, closer to the surface of PSR J1719 Wasnone38b. No heat haze, no wind, just a hard, silent world beneath your boots, if you had boots tough enough to withstand the forces pressing in from every direction. You see, sparkling may be this planet's nickname-worthy trait, but it's what's inside that will make your skin crawl again. Hypothetically, since you'd be flattened before you could even feel fear, this is a place where pressure doesn't just crush rock, it redefines matter. Let's take a slow, terrifying descent beneath that glittering crust. The planet's surface, if it even has a traditional one, is likely smooth but pockmarked by millennia of micrometeorite impacts. There's no atmosphere to burn debris up. If a dust particle hits this place, it hits it. Full force. Each one a tiny hammer blow on a world that's already endured more than most stars. But you go deeper. The first few kilometers down, the carbon is likely crystalline, cool, and compressed, but still in a form that's just barely relatable. If you could chisel some off, you can't. It might flake in shards, but the deeper you go, the stranger it gets. The pressure begins to skyrocket. You're in a place where the weight of the upper layers pushes down with the mass of trillions of tons per square centimeter. Carbon here isn't just under pressure, it's structured by it. The atoms rearrange, bonds tighten, the lattice becomes rigid, tighter than in any earthly diamond. Even light behaves oddly here. Beneath the surface, the refractive properties of the diamond shift. Photons get twisted, paths bend. The internal layers may even act like vast optical prisms, but ones too deep and dark for light to ever escape. At some point, heat becomes a factor too. Although the outer shell has cooled over billions of years, deeper down, internal warmth lingers. The process of crystallization generates heat. So does residual radioactive decay from ancient star core remnants like uranium, thorium, or potassium. That means there could be zones far down where the crystal structure melts slightly. Imagine it, a molten carbon ocean, still under so much pressure that it never boils or bubbles, just flows. Now, let's pause and be clear. These are models. No drill has tapped this world. No probe has returned with a chunk of compressed starlight. But based on physics, on our understanding of white dwarfs, dense matter, and how carbon behaves, we think we're right, or close. And here's a quirky fringe idea. Some theorists suggest that, at truly extreme depths, matter doesn't just compress, it changes phase entirely. Into what? That's part of the mystery. Perhaps an exotic state of carbon, maybe some theoretical form of matter we haven't even defined yet. One that can only exist under pressures found inside, well, inside a diamond planet born from a dead sun. Historians of science will tell you, every century or so, humans find out something they thought was impossible is actually just really hard. So who's to say we won't one day detect these exotic carbon forms in some lab on Earth, or that a spacecraft running on math and sheer audacity won't skim PSR J19 or 1838b and sniff out the truth. Until then, you dream. Imagine the weight. You're falling into a gravity field, unlike anything you've ever felt. The surface gravity of the planet may not be extreme. It might even be similar to Earth's, depending on its exact radius, but the pressure, that's another beast entirely. It builds not just with mass, but with density. You are, after all, walking on what used to be the core of a star. Your bones wouldn't last seconds, not minutes, seconds. Still, in your dream, you keep going, down, past the crystal zones, past the molten rivers, into a core that might be solid metal-carbon alloy, fused by heat and time. Or maybe it's hollow, a ghost bubble at the center, where the matter finally gave way. No one knows. But if you could press your ear against that deep core, what would you hear? Maybe a faint hum, maybe silence, or maybe if the planet is still cooling, you'd hear a slow, deep crack. Not a dangerous one, not a break, just a gentle shifting, a sound that's been traveling outward for millions of years, a farewell echo from a time when this planet still had light. You pull back again, your descent ending. Back to orbit, back to safety. Above you, the pulsar flashes in its perfectly timed rhythm, 31 pulses per second. It doesn't care about your imagination. It doesn't blink. It just spins, watches, and grips the planet like a cosmic leash. The pressure of this place isn't just physical, it's metaphorical. Because this world, this diamond carcass, cannot let go. It is locked in orbit, locked in shape, locked in an identity it didn't choose, a planet made not of soil, water, and life, but of compressed memory, a world that once burned, then froze, then hardened, and now sparkles, a little too quietly. You orbit now, matching the spin of the planet below, like a dance partner gliding in sync. Every 130 minutes, PSR J19 on 1438b completes a revolution around its pulsar, and if your timing is just right, you can feel the rhythm like a heartbeat, or the faint ticking of some impossibly old clock. But tonight, You're not just here to admire the sparkle or dive into its crushed carbon interior. No, tonight you're tracing the path this planet walks its orbit. A loop so fast, so tight, so precise, it borders on the absurd. Imagine this, a gas giant shrunk to the size of Earth, pulled inward until it's just 600 kilometers, barely 1.5 times the distance between Earth and the Moon from its parent neutron star. That's where this diamond world spins. Close, dangerously close. Like brushing shoulders with a buzzsaw and pretending it's a hug. You wonder how it stays together. The answer, mostly, is tidal locking. Just like how our moon always shows us the same face. This diamond planet is thought to have one side always facing its pulsar. That means there's a permanent day side, bathed in invisible waves of high-energy radiation, and a permanent night side, slightly more protected, but no less dead. On the bright side, literally, it's constantly bombarded by electromagnetic radiation, mostly X-rays and gamma rays, not the kind of light that makes sunsets, the kind that makes mutations, cooked circuits, and unplanned disappearances of soft tissue. So yeah, SPF 3000 probably wouldn't cut it. The orbital speed, around 700 kilometers per hour. That's faster than the speed of any object ever built by humans. If Earth moved that fast around the sun, our year would last 37 hours. Good luck planning birthdays. And here's where things get weird. There's no margin for error. If PSR J1719-1438b were just a little closer, the pulsar's gravity would rip it apart completely, shred it into a disk of glowing debris, a sort of grim Saturn ring made of powdered diamond. But it's not, somehow. It hovers just outside the Roche limit, the invisible line between orbiting companion and space smoothie. Why does it matter? Because this is one of the tightest known orbits for a planet-sized object around a pulsar, a relationship so close that astronomers didn't initially believe it. It was like finding a marble doing cartwheels around a neutron star at nose-hair distance. Historians of astronomy love this kind of story. The moment a model breaks, when the math says, wait, this shouldn't even exist, yet here it is, spinning like a jewel in a blender. Some fringe theorists suggest there might be remnants of gas or plasma between the two bodies' streams of material pulled like taffy from the planet's surface, spiraling toward the pulsar. So far, no direct evidence, but the possibility remains. It could be the slowest kind of destruction, a companion being unspooled over eons, layer by layer. You might wonder, does the planet have weather, atmosphere, seasons? Not a chance. At this distance, any atmosphere it once had would have been stripped away by the pulsar's solar wind, more like a solar blast cannon. Really, even the iron in your blood would start twitching under the magnetic fields. You don't just live here. You don't even visit. You speculate from afar, but maybe you could send a robot. You imagine a probe the size of a fridge, with armor thicker than a tank and shielding like a nuclear bunker. It gets dropped from orbit, survives for 3 seconds, and sends back a blurry photo of nothing. Just darkness and a single glitter before its systems fry. Still, worth it. Scientists still argue about whether these close-orbit companions are common. Could it be that pulsars have more of these leftover core planets? We just haven't looked hard enough. After all, we're not talking about gleaming Earth-like worlds. We're talking about collapsed fossils. Not much to shine, unless you know how to look. And speaking of how we look, remember, we found this planet not by seeing it, but by listening. By tracking tiny wobbles in a pulsar's heartbeat. That's like figuring out your washing machine is broken because the vibration pattern of your floor changed slightly. It takes an obsessive amount of precision and, probably, a strong relationship with coffee. This kind of orbit also gives us clues about the past. See, to orbit this tightly, The planet must have once been much larger, a full star. It had to be close enough to spill material into its partner, but far enough to survive the process. As it lost mass, its orbit shrank. This is called orbital decay, and it's like watching a marble spiral into a drain, except that marble used to be a fusion-powered gas ball. The end result, what we see now, a fast, deadly, relentless loop. A jewel caught in a slingshot, a planet frozen in flight, and not a single whisper of atmosphere to slow it down. You hover there, watching the orbit trace itself again. The pulsar flashes, the planet swings, gravity ties them together like a ribbon no blade can cut. And as you drift, you think, if this is what an orbit looks like after the death of two stars, then even in collapse, there's choreography. All right, you've admired the orbit, traced the dense inner structure, and tilted your imaginary head at the weird sparkle that isn't quite sparkle. But let's answer the question you've been holding on to since the beginning. What if you actually landed there? What if you could take your sleek little space capsule, match the blistering orbital velocity, deploy some impossibly durable landing gear, and gently, very gently set foot on the diamond planet? Brace yourself. You probably wouldn't love the experience. Let's assume, for a moment, you're wearing a sci-fi grade suit made of fantasy materials. It absorbs radiation, resists extreme pressure, and keeps your innards from rearranging. Even with that, your chances of surviving are basically zero. But we're already suspending the laws of physics just by putting you on the surface. So hey, might as well walk it through. As your landing gear deploys, you begin to feel gravity, not the crushing weight of a black hole. No, surprisingly, the surface gravity might not be much stronger than Earth's. That's the weird thing, because while the planet is extremely dense, its mass is still only about Jupiter's, and it's small enough that you might be able to stand, sort of. You step out, your boot lands with a crisp, unnatural crunch. It doesn't feel like rock, not sand, not metal, more like stepping onto a frozen lake made of glass and ancient time. Every step echoes in your mind with the knowledge that beneath your feet lies thousands of kilometers of solid, pressurized carbon likely layered with crystal structures unlike anything you've seen. The ground doesn't shift. It doesn't dust up. It just holds immovable, eternal. But then there's the light. It's dim. The pulsar doesn't emit warm rays. It doesn't light up the planet in cozy golden tones. It spits out high-energy radiation, mostly invisible to your eyes. But your suit, remember, it's the deluxe kind. Lets you see the pulses. Every 0.0032 seconds, the pulsar flashes, and the faintest glitter dances across the horizon like a ghost, winking in Morse code. It's the loneliest sparkle in the universe. You decide to walk because, well, you're already here. But you notice something strange. There are no features, no mountains, no valleys, no rivers, just slight undulations, rolling hills of diamond crust, formed maybe by ancient tectonic shifts before the planet fully crystallized. Or maybe, more unsettlingly, there were never geological events to speak of here. No crust-mantle core divisions, just one massive, unified body of carbon under pressure. Still, you trudge onward. The weirdest part, the sound or lack of it, even inside your sealed helmet, there's nothing, no wind, no seismic vibrations, just the mechanical beat of your own breathing. This planet isn't silent in the way a forest at night is silent. It's silent in the way a vacuum is silent. It doesn't even remember sound. And then comes the pressure. It doesn't crush you all at once. It pushes on you, slowly, perpetually, like the weight of memory on your shoulders. Your suit's pressure regulators kick in, but you feel it anyway. Your joints ache, your muscles tighten, as if the very planet is trying to tell you, you don't belong here. If you were here without protection, you'd be dead in less than a second. Your blood would boil not from heat, but from lack of atmospheric pressure. Your cells would rupture, your body would implode, and your bones would compress until they fused into something geologists would stare at for weeks and say, "That used to be a person." Comforting. Historians have long used fictional planets to reflect human emotion, like Mars as a symbol of war or Venus for love. But this, PSR J269 J138B, this is finality. This is what a world looks like after everything ends. Yet something still stubbornly remains. And still, you look up, the sky is pitch black. No atmosphere to scatter light, but the stars, they're vivid, sharp enough to prick your imagination. And straight ahead, oh, glowing with its pulsing rage, is the pulsar. Every flash illuminates the surface with harsh, bluish radiation, not enough to see, but enough to sense. Every flash says, "Still here, still watching, still hungry." You kneel, you touch the ground. It's warm, not hot, but warmer than you expected. Residual heat from the planet's deep interior, still bleeding out after billions of years, like the last sigh of a campfire long gone cold. You wonder, is it lonely? Probably not. It's a rock. But you feel something in the stillness, something in the fact that no one, not one single life form has ever stood here before. Not now, not ever. Fringe philosophers have pondered, if you stand on a dead star and no one hears you scream, did you still go viral? The answer is probably no, but the idea lingers. And just as you start to head back to your craft, you feel a rumble. Not a quake, just a soft shifting, like a sleeping world rolling over in its endless dream. Maybe it's crystallizing further, maybe a layer just compressed. Maybe a cosmic ray just tickled something loose in the core. You don't know. And that, weirdly, is the point, because this isn't a place of answers. It's a place of silence, of permanence, of pressure. And the fact that you're here, even just in your imagination, means the story still matters. You step back from the diamond surface, at least in your mind, and drift again in the safe stillness of orbit. One breath, then another. Below, the dead world spins in silence. Above, the pulsar flashes like a lighthouse that forgot how to stop. But something else catches your attention. Now, something unexpected, subtle, and deeply weird. The way this planet sparkles, not in the way a jewel sparkles under candlelight. There is no light source here, gentle enough for that. No flickering flames or sunshine to glint off facets. And yet, it sparkles in radio waves, in gamma flashes, in the invisible throb of electromagnetic fury. Let's talk about why. You already know. PSR J719-1438b is locked in orbit with a millisecond pulsar. That thing spins faster than a dentist's drill. And like all pulsars, it emits beams of radiation from its magnetic poles. These beams sweep across space like laser pointers gone mad. And here's the beautiful, terrifying part. When those beams hit something, even a sliver of material, they bounce. Not like a ball off a wall, more like microwaves rebounding off a disco ball made of gravity and time. Now imagine this. You're floating between the pulsar and the planet, tuning into its radio signal. Every pulse hits the surface of PSR J1719 or 238b and bounces, reflects, skims the crystal crust, which acts like a mirror, except one designed by physics instead of people. Astronomers believe the planet's reflectivity, or albedo, is unusually high. That means it reflects a large portion of whatever energy slams into it. X-rays, gamma rays, high-energy particles. Not only does that help confirm its structure, but it also enhances the sparkle, not visibly, to the naked eye, but in data. One signal reflects back slightly out of sync with the original pulse, then another. It's like listening to the same heartbeat echo through a crystal cave. The sparkle is data. It's not sparkle for beauty. It's sparkle as physics. And that brings us to something incredibly cool, literally and figuratively. When scientists talk about planets like this reflecting pulsar beams, they aren't just describing visual effects. They're describing how we found it. The diamond planet doesn't announce itself with glowing lights or heat signatures. It reveals itself by messing with a rhythm. Imagine your favorite song. You play it so many times, you start to know every beat. Then one day, there's a hiccup barely perceptible. Like a drum coming in half a second late. You rewind. It's subtle, but it's there. That's how astronomers felt when they studied PSR. Jacoy 719-1438. The pulsar's timing was off. Just slightly, just enough to suggest that something was bouncing those pulses back at, not disrupting them but nudging them with enough precision. You can use these shifts to calculate the object's size, mass, and distance. It's like radar, but cosmic and extremely patient. Fringe thinkers have a field day with this. Some suggest that advanced civilizations could intentionally modulate pulsar beams, creating artificial timing shifts to send messages across galaxies. It's purely speculative, of course, but it's fun to imagine. What if PSR, JWA 1719-1438b, wasn't just a planet, but a signal amplifier, a natural object repurposed by alien engineers to bounce cosmic telegrams through deep space? No evidence, obviously, but the sparkle makes you wonder. The idea of mirrors in the sky isn't new. Ancient cultures looked up and believed the stars were watching. Some thought they were eyes. Others thought they were jewels pinned to a dome, reflecting divine light. And in a way, they were right, because here you are, staring at a jewel-like world that does reflect something greater. The death rattle of a neutron star. This isn't a planet that glows. It's a planet that echoes. The light you'd see with human eyes would be minimal, just a faint gunmetal sheen. But if your eyes could see in radio, X-ray, or gamma spectra, this place would look like it was buzzing, shimmering in slow-motion static. And here's something truly wild. If you were floating here with a radio receiver, and you tuned it just right, you could hear the pulses, not as voices or music, but as rhythmic blips. Ba-dump, ba-dump, ba-dump. And the ones that bounced off the diamond planet, they'd come in slightly delayed, slightly distorted, a second beat, a ghost echo. You've probably never imagined a planet as an instrument before, but this one. It plays back up to a dying star's final concert. Historians still debate how far we can push pulsar science. Could we map entire planetary systems using nothing but timing delays? Could we build interstellar GPS using pulsars as cosmic lighthouses? It's possible, and if so, this diamond planet might be more than a relic. It might be a signpost, a node in some future network of space travel and distant communication. But for now, it's just sitting there, reflecting, spinning, sparkling in all the ways you'll never see, but somehow still feel, because you do feel it. Not with your eyes, not even with your ears, with your awe. You drift back a little, the planet now a shrinking glint beneath your boots, a lonely shimmer in the vast dark. But as your gaze lingers, something ancient stirs, not just in your mind, but in the collective memory of your species. Because as strange and futuristic as this place seems, its sparkle touches something old in us, before telescopes, before science, before language even. Humans looked up at the night sky and saw jewels. You've probably done it too, called a bright star glittering. Describe the night as studded with light. It's poetic, sure, but also oddly instinctive. The universe sparkles, so we assumed the sky was full of gems. Turns out, that instinct wasn't entirely wrong. Let's rewind the clock, not by billions of years, like we did before, but just a few thousand. In ancient Mesopotamia, priests believed the heavens were made of lapis lazuli, a sacred blue stone flecked with golden pyrite. They mapped the stars with that idea in mind. The sky wasn't air, it was stone, hard, precious, divine. Egyptians saw Sirius the dog star as a literal gemstone in the goddess Isis's necklace. Greeks said the gods had sewn jewels into the heavens to remind mortals of their place. And in the Americas, the Incas imagined stars as gold nuggets hammered into a vast cosmic blanket. Even today, our metaphors haven't changed much. We say people shine like stars. We give diamond rings to mark eternity. And when something's breathtaking, we say it's out of this world. It makes you wonder, did we dream of diamond planets long before we knew they existed? Historians of language have traced certain root words back thousands of years. Words like brilliant, radiant, glory, all tied to the concept of shining. And some fringe theorists suggest this deep connection between sparkle and significance isn't random, that early humans associated shining things with truth, immortality, and power because those things, sunlight, starlight, firelight, meant survival. Now you look down at PSR, J19 or 1438b again, and realize it's not just a geological oddity, it's a symbol of endurance, of transformation, of the fact that even in a universe built on decay, something can survive not in flames, but in crystal. But not all stories of diamonds are lovely back on Earth. Diamonds have been used to celebrate love and status. Yes, but they've also sparked wars, funded brutal regimes, become currency for suffering. The term blood diamond exists for a reason. It's a reminder that beauty, unexamined, can be dangerous. You imagine, for a moment, a civilization advanced enough to visit PSR J19 Vort 38b. Would they mine it, harvest its carbon, slice it into slabs, and wear them as trophies? Or would they stand in reverent silence, staring at a world that defied death? Some philosophers believe humans project meaning onto space because we have to. The void is too cold, too vast, so we fill it with symbols. This planet, we call it diamond, not just because of its composition, but because that word means something to us. Permanence, clarity, value. But maybe, just maybe, to the universe, it's just a rock, a leftover, a thing. Still, you can't help it. You imagine ancient storytellers sitting by firelight, looking up and saying, "See that twinkle? That's where the gods keep their treasure." And they weren't wrong. Not entirely, because right now, you're staring at treasure. Not the kind you can spend, not the kind you can cut, polish, and wear, but the kind that reminds you just how vast and weird and heartbreakingly accidental your existence is. And here's one more poetic kick in the teeth. This isn't even the only diamond world. There are others. Suspected ones, 55 Cancri, for example, a planet roughly twice Earth's size, orbiting so close to its star that one side is perpetually scorched. Some models suggest its interior might also be carbon-rich, maybe even crystallized. It's not confirmed, but the possibility lingers. Just imagine a whole system with multiple glittering corpses locked in tight orbits, whispering heat into the dark. It's not science fiction. It's science waiting, and it brings us back to the oldest human impulse to point at the sky and say, that one's mine. Even though we'll never reach it, even though it doesn't care. But it does shine. Not for us, but still, it shines. And in that shine, we find meaning, we find myth, we find a reason to stay awake a little longer. You're still out there, drifting quietly. The diamond planet is now a pinprick below you, still locked in its orbital waltz. The pulsar beside it flickers steadily, like a cosmic engine refusing to stall. And while your view may be vast, you begin to zoom in not with your eyes, but with your curiosity. Because how do we know all this? How do we know about a planet that no human has ever seen, that doesn't glow, doesn't reflect sunlight, and doesn't send postcards? The answer is both wildly technical and strangely beautiful. We listen to stars the way blindfolded musicians play piano, by touch, by timing, by pattern. Let's start with the heartbeat. Pulsars, as you know by now, are neutron stars, the collapsed cores of supernovae. They spin rapidly and emit beams of electromagnetic radiation from their poles. If Earth happens to line up with those beams, we detect them as pulses like a lighthouse beam sweeping across the night sea. This is called a pulsar signal, and it's one of the most precise rhythms in the known universe. Now enter PSR J1619 do Homos Monte 38. In 2011, a team of astronomers using the Parkes Radio Telescope in Australia noticed something weird. This pulsar's pulse timing was just slightly off, not randomly, not chaotically, but predictably, as if something was tugging on it, delaying the signal, nudging the heartbeat. It wasn't a glitch, it was a whisper from something small, dense, and close. From that whisper, scientists did the cosmic equivalent of crime scene reconstruction. They mapped out the pulsar's motion, calculated the tug, and inferred the mass and orbit of the mysterious object. This method is called pulsar timing, and it's accurate down to microseconds, like detecting a fly landing on a watch hand from 1,000 kilometers away. Once they had the orbit and mass, the rest followed like clues in a locked room mystery. The object was too massive to be a rock, too small to be a star, and too dense to be anything but a remnant core. Based on the mass-radius ratio, its average density came out to over 23 grams per cubic centimeter, about 20 times denser than lead. Lead. Imagine a world denser than lead, made of diamond, circling a dead star. You can't see it through a telescope. Not directly. You know it's there because its gravity leaves fingerprints on time. Historians often refer to Galileo's telescope as the beginning of modern astronomy. But these days, the real revolutions come not from looking, but from measuring. From vibrations, pulses, and light curves, from tiny wobbles and delayed flashes. Take this. We now detect exoplanets by watching stars dim ever so slightly as planets pass in front of them, or by measuring how their light shifts due to a gravitational tug. We call it the Doppler method. And while that works well for sun-like stars, it doesn't help much with dead stars like pulsars. That's why PSR J17191438b is special. We didn't see it dim anything. We didn't see it reflect light. We saw it warp time. There's something humbling about that, isn't there? You float in space, remembering that what your eyes miss, your instruments can still catch, that not all beauty is visible. Some of it is timed, subtle, and encoded in rhythm. Fringe theorists like to push this further. Some wonder if we could one day build entire space navigation systems using pulsars like cosmic lighthouses or interstellar GPS satellites. They'd be immune to tampering, anchored to physics itself, and accurate across hundreds of light years. Your ship would just listen. And if that's possible, then maybe one day, PSR J1719 or 1438b won't just be a curiosity. It'll be a landmark, a node, a beacon that says, here, this is the place where time bends just slightly offbeat. And you're reminded this isn't science fiction. We've already built spacecraft that use pulsar signals to navigate. In 2017, NASA's NICER mission tested this exact concept aboard the International Space Station. They called it Sextant because, of course they did, and it proved that, yes, you can use pulsars as interstellar compasses. So the tools are coming. The signals are here. All we need is the curiosity to follow them. You look down once more at the diamond planet. It says nothing, reflects nothing back. You can see, but it pulls not just on the pulsar, not just on math, but on your wonder. And maybe, just maybe, that's how we found it in the first place. Not because it sparkled, but because we couldn't stop asking what made the pulse skip. By now, you've wandered this planet in every way but literal. You've stood on its surface, imagined its birth, mapped its orbit, and even eavesdropped on its pulses. But let's take a different kind of journey tonight. One that peers not into the planet itself, but into the minds of those who studied it. Because let's face it, how we know what we know about PSR JWUS N719 or 1438b is almost as fascinating as the planet itself. Let's revisit that iconic moment in 2011 when researchers at Swinburne University of Technology, using the Parkes Radio Telescope in Australia, first spotted something strange in the pulsar's rhythm. They didn't jump up and shout, "We found a diamond planet." That came later after a lot of silence, skepticism, and, of course, spreadsheets. It began with timing. Pulsars, as you now know by heart, don't pulse randomly. Their signals are so precise, they make atomic clocks look like sundials. But PSR J1 14 through 8, its pulses were drifting not wildly, but subtly, predictably, like a dancer slightly tugged off step by an invisible partner. That partner, of course, was the planet. By mapping the delay in the pulse arrival times, the team deduced that something with about the mass of Jupiter was orbiting the pulsar every 2 hours. So far, so good. But here's where the method shines. They also realized the object had to be incredibly dense. Otherwise, it would have been torn apart by the pulsar's tidal forces at that distance. Cue the math. You can almost picture it chalk on a whiteboard, circles and Greek letters. Someone standing too close to the coffee machine muttering, "Wait, that can't be right." Because the density they calculated wasn't just unusual, it was absurd. Over 23 grams per cubic centimeter. That's denser than any known gas giant, denser than rock, denser than metal. What's left? Carbon, under extreme pressure. Now, it wasn't a leap to suggest diamond. After all, diamond is what carbon becomes when crushed. It wasn't wishful thinking. It was thermodynamic inevitability, but still, calling it a diamond planet raised some eyebrows. Mainstream scientists hesitated. Critics pointed out that we couldn't directly observe its surface, so that it might not be diamond in the gemstone sense, but more like ultra-compressed carbon in various crystallographic forms. In short, it could be diamond, but don't go shopping for earrings just yet. But here's the thing. Astronomy is always a dance between certainty and wonder. Historians of science often describe breakthroughs as moments of elegant guessing, backed by brutal math. This was one of those moments. The diamond planet wasn't discovered in a telescope. It was discovered in a spreadsheet full of errors, all perfectly timed. And this wasn't the first time scientists used odd pulses to find strange things. In fact, pulsar timing arrays are now one of our best tools for detecting gravitational waves, those elusive ripples in space-time, predicted by Einstein and confirmed in 2015. Imagine, we can now watch stars wobble from galaxies away and measure that wobble using dead stars spinning 700 times per second. There's a quiet poetry to it. We used to think astronomy was about looking. Now we know it's just as much about listening. Some fringe scientists and futurists even think this is just the beginning, that pulsars, planets, and their timing patterns could form the basis for interstellar networks, not just for navigation, but for communication. Imagine civilizations pinging each other across the cosmos using neutron stars as nodes. Their language wouldn't be words, but beats, pulses, deliberate hiccups in a cosmic rhythm, a kind of Morse code, but on a galactic scale. Now, there's no evidence that PSR J171914 through 8b is part of anything artificial. But the way we found it by listening, by decoding irregularities, feels like training for something bigger, something we might not even recognize yet. Historians still argue whether astronomy should be more cautious or more poetic. Should we call this a diamond world or just an ultra-dense carbon remnant? Should we romanticize it or stick to the math? But maybe that's a false choice, because if science didn't make room for imagination, we never would have looked here in the first place. The planet is real. The sparkle is theoretical. But the curiosity, that's entirely human. So you float in your imaginary ship, watching the pulses blink, counting each one, knowing that with every tick of cosmic rhythm, data flows, knowledge grows, and a quiet little planet born from a star, polished by gravity, found by math, keeps spinning, unaware that anyone cares. But you do, because somewhere in that dance of pulses and numbers and speculation, you heard a story, and once you hear it, you can't unhear it. You close your imaginary laptop, if you even brought one, and drift farther from the diamond planet, not because you're done with it, but because now you're asking a new question, a question driven by the same impulse that made us reach for the stars in the first place. Could we bring it back? Could we harvest this cosmic gem? Because let's be honest, at some point in this journey, probably when we called it a planet-sized diamond, your inner goblin whispered, "How much is that thing worth?" The short answer, more than the global economy. The long answer, let's talk about cosmic mining and why you'll probably die before cashing in your interstellar diamond. First, the math. The estimated mass of PSR J11.19.38b is about that of Jupiter, roughly 9x1027 kilograms. If most of that mass is crystalline carbon, we're looking at more than 1030 carats of diamond. For perspective, Earth's entire diamond production in human history is under 1 billion carats. The market would crash faster than you on this planet's surface. That's assuming, of course, you could mine it. You can't, not with anything we've got. Not with drills, robots, or wishful thinking. You'd need technology that doesn't exist and energy on a scale that makes entire national power grids look like AA batteries. And even if you had that tech, there's the problem of getting there. PSR J1619.1.38 is 4 light years away. With current spacecraft, it would take tens of millions of years to reach it. By the time your mining ship arrived, you'd either be dust or part of a species that forgot what diamonds even were. Fringe technologists sometimes throw around ideas like warp drives or wormholes, but those remain comfortably speculative. Even the most optimistic blueprints for interstellar travel keep us within our own stellar neighborhood, not light millennia deep in the galactic suburbs. But let's say you solved that. You arrived. Your mining bots got to work. You somehow carved off a truck-sized slab of interstellar diamond. Congratulations! Now all you have to do is escape the planet's gravity well, survive the pulsar's radiation, navigate a return journey through interstellar space, re-enter Earth's atmosphere, and explain to customs why you've got a 4-ton gem strapped to your ship. Also, by the time you got home, someone would have probably already printed diamonds using nanotech and sold them as NFTs. In short, you're not getting rich, but that hasn't stopped the dreams. Even today, private companies are planning missions to mine asteroids in our solar system. Many of them contain precious metals like platinum, gold, and rare earth elements. It's not just a sci-fi daydream. There are official budgets, engineers, and launch windows. It's hard, yes, but it's possible. What's not possible? Hauling back a planet-sized diamond. Which brings us to the real cost of cosmic luxury, not in dollars, but in perspective. You can't own this world. You can't sell it. You can't even touch it, but you can know it. You can tell its story, and sometimes that's the more powerful kind of wealth. Historians of exploration remind us that humans don't cross oceans because they're filled with gold. They cross them because something's there, something strange, something that wasn't ours, but now lives in our imagination. Some fringe philosophers go further, suggesting that objects like PSR J1719 or 438b exist not just physically, but mythologically. The moment we name them Diamond Planet, Lucy, 55 Cancri, they become symbols. They live in our dreams, not just our databanks. So you drift, thinking, would owning this planet make you happy? Or would it just make you responsible for something you can't possibly control? Would you cut it into smaller pieces, display it in museums, hide it in a vault? Or would you leave it there, spinning, quiet, unspoiled? Because maybe the real value of PSR J1719 1438b isn't in what it's made of, but in what it survived. It was a star once. Then it wasn't. Then it was almost destroyed. But it wasn't. And now it glitters not for us, but despite us, a reminder that not everything bright must be bought. Not every treasure must be claimed. Some just need to exist so we can look, wonder, and let our greedy little inner goblins whisper. What if? You're starting to feel the drift now, not in space, but in thought. The Diamond Planet, the tight orbit, the cosmic heartbeat. It's all begun to blur into something stranger because after all this time among stars and shattered suns, you start to remember where you came from. Home, Earth. So tonight, let's compare the alien with the familiar. Because while PSR J1719 1438b is beyond bizarre, we actually have our own diamond drama playing out. Right here on the ground. Let's start with the basics. Diamonds on Earth are formed deep in the mantle, about 150 to 200 kilometers below the surface. There, carbon atoms get squished under extreme heat and pressure enough to overcome their natural repulsion and bond into that rigid, crystalline lattice we call diamond. They ride to the surface during volcanic eruptions, especially in rare igneous rocks called kimberlite pipes. We dig, we cut, we polish, and voila, jewelry, tools, drill bits, engagement rings, marketing. A lot of marketing. The story of Earth's diamonds is tangled up in history. For centuries, they were the gems of emperors and kings, symbols of strength and invincibility. The word diamond itself comes from the Greek adamas, meaning unbreakable, poetic, a little misleading. Then came the 20th century, and that's when things got wild. De Beers, you've probably heard the name. They didn't just sell diamonds. They sold the idea of diamonds. They turned a relatively common stone into a global obsession. A diamond is forever became the slogan that redefined love, commitment, and late-stage capitalism. Prices soared, minds expanded, and suddenly, what had once been a curious geological quirk became a multi-billion-dollar identity crisis. But here's the kicker. Diamonds aren't actually rare, not geologically. We can make them in labs now, flawless ones. Perfect lattice, no inclusions, grown in weeks, not eons. They're used in everything from electronics to scalpels, and most people can't even tell the difference. So what keeps Earth's diamonds valuable? The story, the symbol, the human need to assign meaning to sparkle. Sound familiar? Historians argue that diamonds are the most successful myth ever attached to a rock. They've stood for purity, status, eternity, and wealth. They've been smuggled, stolen, fought over, and yet, for all that drama, they're just carbon. Same as graphite, same as pencil lead, same as you. Technically, which brings us back to PSR J1719 or 1438b. Same material, different context, and yet, strangely similar meaning. because when scientists called it a diamond planet, they weren't trying to hype it for resale, they were speaking symbolically, trying to translate the incomprehensible into something relatable, just like De Beers, in a way only with less champagne and more data. You see, Earth's diamond economy is based on limitation. Space's diamond drama, based on transformation. One is artificial scarcity, the other is cosmic inevitability. And yet, both fascinate us. One fringe school of thought suggests that if humanity ever becomes spacefaring, really spacefaring, we'll have to redefine value entirely. Gold, platinum, diamond, these are all precious because they're hard to get. But what happens when you can mine asteroids by the truckload? When you find planets made of crystal? When your ring is less valuable than the asteroid you parked your spaceship on? Historians of culture wonder if we'll shift to experiential value instead. You won't brag about what you own. You'll brag about what you've seen, where you've gone, what your mind has touched. In that future, PSR J1719-1438b isn't a source of riches. It's a rite of passage, a story. Did you go to the diamond world yet? Only from orbit. We weren't cleared for landing. Lucky. I caught a pulse reflection while passing Saturn's edge. You smile, imagining it, but back here, in the now, Earth's diamond politics rage on. There are still mines run under brutal conditions, still blood diamonds trickling into markets, still fights over certification, ethical sourcing, and whether a lab-grown gem counts as real. And yet, the sparkle persists. We still propose with them, still cry over them, still hold them up to the light and say, look, it shines, same as we do with PSR J1719 or WAM-SONDE-TORISHOB, same as we do with stars, same as we do, really, with anything we don't fully understand, because sometimes a sparkle is just a sparkle, but sometimes it's a reminder that beauty exists in pressure, that stories crystallize under time, that carbon, whether in your chest or a crushed star, can become something unbreakable. You've come a long way tonight, through collapsing stars, invisible pulses, crushing gravity, and glittering symbols that reflect everything from ancient myth to cold physics. And now you hover here, one last time, above a world that didn't ask to be called beautiful, but somehow became the most poetic remnant in the galaxy. This is PSR J1719-1438b, a planet made not of ocean, wind, or cloud but of carbon, crystallized under pressure so intense it would crush mountains into sand, born from a star, carved by a pulsar, and left spinning quietly in a death dance orbit with its devourer. But there's one more idea we haven't touched yet, one that floats at the edge of science and philosophy. It's not about how the planet formed or what it's made of. It's about what it means, because for all the technical wonder here, for all the talk of density, crystallization, and orbital decay, the most human part of this story is the part we bring to it. Oh, you look down now, and it's just there, spinning, quiet, indifferent. But in that indifference, we find reflection, a planet that should have been destroyed, but wasn't. That should have disappeared, but didn't. A collapsed core, hardened into something that can never burn again, but can still sparkle, even if no eye sees it. There's something haunting in that, something reassuring. Too, we spend so much of our lives trying to make light. We build homes, cities, memories, always chasing warmth, always reaching for brightness. And sometimes we forget that some of the most remarkable things in the universe were formed not in creation, but in survival. PSR J1719-1438b is a monument to endurance, to pressure, to quiet. It reminds you that there are places where the rules get rewritten, where stars die not with fire, but with stillness, where death doesn't mean disappearance, it means transformation. and where even the remains of something long gone can echo across space, time, and imagination. Historians still debate the sparkle. Some say it's a convenient metaphor. Others argue it's a glimpse into a phase of matter we barely understand. And a few believe that, even if we never see it with human eyes, the fact that we know it's there changes us, because now, when you look up at the night sky, you know, somewhere, 4.0 light years away, there's a planet spinning around a dead star. It pulses like a second hand on the galaxy's clock. It sings in radio. It shines in silence. It endures. And even though it will never know you or care about you, it exists. And somehow, that makes everything feel just a little more possible. You take one last breath. Let the image burn into your memory. A diamond the size of a world, spinning forever in the dark. Proof that even the smallest leftover can become something radiant. You close your eyes now, and the pulses fade. The diamond planet drifts behind the curtain of sleep, its orbit smooth, its silence complete. No roaring engines, no crashing waves, just the soft, steady beat of a collapsed star and the glint of a crystal sphere that once was light. Let the pressure of that place ease from your shoulders. Let its vast, distant weight stay in the sky where it belongs. Your bed is soft, the air is still, and the only gravity pulling on you now is the one that tells you you are here, you are safe, you are small, and that's okay. You don't need to understand every equation to feel wonder. You don't need to mind the planet to find value. You only need to let the story settle into your mind like dust on a windowsill. Soft, gentle, undisturbed. Let your breath slow, matching the rhythm of the pulses, not 31 per second, just one. In the one, out. You are not a pulsar. You are not a planet. You are something rarer, something fleeting, and still, something part of it all. Sleep comes like orbit, slow, predictable, beautiful. Let it take you, and if you dream, let it be of stars. Let it be of sparkle. Let it be of diamond hearts and carbon ghosts that still shine, even when no one is watching.